we can now calculate the moment of inertia for the rotating wheel. Remember that on the wheel, and let's look at the wheel here, we had 4 masses, 1, 2, 3, 4, at a maximum distance from the center of rotation, and then 4 in the middle and 4 nearest. So we had 4 bolts at 9.5 centimeters from the center. We get that simply by measuring the distance from the center of the axis to the center of the outer bolts. And similar measurements tell us that there are 4 bolts at a 6.6 centimeter distance and 4 at a 4.9 centimeter distance. So that each bolt has a mass of 18, well, not so that, but we measure each bolt and the mass of each is 18 grams. Now we calculate the moment of inertia contribution, the mr squared, for a mass of 18 grams at a distance of 9.5 centimeters from the center. Well, that's fairly simple. Mr squared is 1600 grams centimeters squared. Just multiplying this by the square of this. Now we want to convert that to standard MKS units, and we do, and we say that that mr squared is actually 0.0016 kilogram meters squared. For the 18 grams at a radius of 6.6 centimeters, mr squared is 0.00007 kilogram meters squared, and you can verify that calculation. You should. It's a simple enough calculation, doesn't take long. Punch it into your calculator. We've done some rounding off here. We're only doing an approximation. You can get it as accurate as you want. And then for an 18 gram mass at 4.9 centimeters, mr squared is 0.00004 kilogram meters squared. Now notice a couple of things. This 4.9 centimeters is more than, well, the 9.5 centimeters is less than twice as far as the 4.9 centimeters from the center. But the moment of inertia here appears to be about 4 times as great as the moment of inertia here. So the distance from the center has a lot to do with moment of inertia. As distance from the center increases, the moment of inertia of a given mass increases drastically. That's because r is being squared. You want to think about that, squared proportionality. In any case, if we want the total moment of inertia of these bolts, we do the calculation shown here. Okay, I is the total, the sum of all the mr squareds. And since there are 4 bolts at 9.5 centimeters and each one has 0.00016 kilogram meters squared moment of inertia, we're going to take 4 times that, and we're going to add 4 times the moment of inertia of the middle masses and 4 times the moment of inertia of one of the inner masses, and we get the total moment of inertia of 0.0011 kilogram meters squared. That's the moment of inertia of the discs. I'm sorry, of the bolts. We've ignored the moment of inertia of other parts of this system. We've ignored the styrofoam. There's a lot of styrofoam there, but styrofoam's pretty light. The total mass of styrofoam here is probably not more than the mass of 1 bolt. We've ignored the moment of inertia of these bolts and washers in toward the center. That's pretty safe because these are so close to the center, they don't have much r. So when we do mr squared, there isn't much there. That's not going to be significant at any level with anything we can measure. If we measure carefully, we might be able to tell the difference due to the weight of the styrofoam. And then there are other things like in this system, remember, we had a thumbtack. See the thumbtack here. The thumbtack was holding the thread, which you might be able to see, which was holding the washers. Okay? Kind of dangling there and not being focused on. So there are other contributions to the moment of inertia, but this is the main contribution, the contribution of the bolts.